taking it up from page 13 of the notes. Okay, last time, remember, we looked at the small increments formula, which to briefly remind you, which for two variables was this expression in equation 1.56 there. This is for a function of two variables. And this, what we call the small increments formula, I mean, that's kind of more or less not a universal name for it, or I think it's just what I like to call it. Small approximations formula, or approximate formula. Or it's a bit more technical and precise. It's the linear approximation to a function in two variables. And then by generalization to a function in any number of variables. It shows how the partial derivatives of the function with respect to x and y, two variable case, how they provide the coefficients in that linear approximation to the function. Okay, so we looked at that last time. We looked at a few examples. And we're going to build on it today, because today we're going to look at the chain rule. So first of all, just a reminder, I mean, we already know about something called the chain rule in functions of a single variable. So we'll just bring that back to our minds. So the chain rule for a function of a single variable, if we have a function y equals f of x, but what if the argument x is itself a function of another variable? If we have some expression which relates x, which gives x as a function of some other variable, say time t. So y is a function of x through the function f, and x is a function of t through the function g. But then we have this problem that what if we want the derivatives of y with respect to t? Okay, because ultimately y depends on t, but through its dependence on x. So then the question is, well, how do you express the derivative of the first variable y with respect to t? How do you express it in terms of the derivatives of the two functions f and g, which combined together through composition give the dependence of the variable y on the variable t? So that's something that the chain rule provides for us. We use it in situations where we have like a function of a function of a function of a function, or composition of functions. How do you express the derivative of one variable with respect to another in terms of the various functions in the composition? So we kind of think of it commonly in the form of these two equations. So you have firstly dy dt is the product df dx times dg dt. Or using the other kind of superscript notation, you could have y prime of t on the left-hand side. That would refer to the derivative of y with respect to t. And that's equal to f prime of x of t multiplied by g prime of t. I think the second form, I prefer the second form of the notation. It's slightly more meaningful, and it still indicates the use of composition. And it also makes it clear where the two derivatives, f prime and g prime, get evaluated. So f prime is evaluated at x of t, and g prime is evaluated at t. So that was the chain rule for functions of a single variable. And a common use of this is when you've got a complex formula expressing a function. So the formula is built up out of lots of standard functions combined together, or composed together, then obtaining derivatives of the overall composition function. Okay? We exploit the chain rule to build that up out of derivatives of the component functions. So what we want is we wish to get the same tool for functions of more than one variable. So what ideally, this is the kind of thing that describes here what we want. Suppose we have a variable y expressed as a function f of more than one variable. So variables x1 through xn. That's equation 1.74 there. So we've got some system of coordinates x1 up to xn, and they're a system of coordinates for the space Rn, for the domain of the function f. Okay? But then we might want to switch to a new set of coordinates, say z1 through zn for Rn. And we'll have some kind of relationship between the old coordinates xi and the new coordinates z. And those will be given by transformation functions, referred to here as ui. So then what we want is to be able to express the derivatives of the function f with respect to the new variables, or is there, how do we express the derivative dy dz? Okay, so y is related to the xi through the function f. How do we, and the xi in turn related to the zi's, how do we get partial derivatives dy dz? Out of the known, or the kind of known derivatives df dx and the derivatives of the transformation function dy. Now, before we jump into developing the theory of that, let's just look at a concrete example of two coordinate systems that we might want to talk about. So this is an example 1.9. I don't know if I'm going to add too much more to it here on the page, but just to talk through it. So consider the polar coordinate system. So this is just to get a concrete example in our minds of a multivariable space, so looking at R2 and two different coordinate systems. The polar coordinates for R2. So there's R2 with the x and y coordinate axes. There's a point P. And the polar coordinates are a really nice way of locating where the point P is. And for certain applications, for certain uses, it's extremely convenient. So you locate where the point P is in the plane by specifying two things. Its distance from the origin, its radius, the radial distance of the point P from the origin, and then by giving this polar angle theta, which is the angle that the radius makes with the positive direction of the x-axis. Okay. So any point P in R2 can be located by a pair of coordinates r theta, where 0 is less than or equal to r, and the radial distance can go up to any value, and say 0 is less than or equal to theta, strictly less than 2 pi. Okay, you need to have a full circle's worth of angles to describe the location of points in the plane, in R2. Okay, and well, with some ambiguity about the origin. Uncertainty about the origin, because the origin, if you say that the radius is 0, you can kind of specify any angle if you like, because it's not off the origin, it's just on the origin, so the angle kind of becomes a bit meaningless. Ambiguity, it's maybe not so precise or maybe not so simple as one point has one pair of coordinates. Everywhere away from the origin, one point will have one unique pair of coordinates, r theta, with the r and theta in that range. Consider the polar coordinates. Of course, we also have our more familiar Cartesian coordinates for the point, the coordinates x and y, which also locate the point. So then there's the question: how are the Cartesian coordinates x, y related to the new set of coordinates, the polar coordinates r theta? Well, we can kind of see how they're related on the diagram, but we can express that precisely to the use of transformation functions. So do this using transformation functions. functions that describe the transformation from one coordinate system to the other. I'm just more or less repeating what's in the notes there, but maybe giving a little bit more narration to it. So on the one hand, we can express x and y as functions of r and theta. There's an obvious right-angled triangle up there, this right angle here. You've got the hypotenuse is r, you've got that angle theta. The other two sides of the triangle are x and y. So by using trigonometric functions, you can express the relationship between x and y like that. Sorry, the relationship between x and y and r and theta using these two equations. Or you can go in the other direction. So what do I mean by that? Going in the other direction. In the other direction, so this is like x as a function u1 of r theta, and y as a function u2 of r theta. So you could say u1 and u2 are the transformation functions. Or you could go the other way around. What are r and theta in terms of x and y? So if you know the x and y, how do you obtain the r and theta? Those first two equations tell you that if you know the r and theta, then you can calculate the x and y. Well, r, of course, is the square root of the sum of the squares of x and y. That's how you express the radius in terms of x and y. And the angle theta you can express using the inverse tan function. So that can be arc tan of y over x. The inverse tan function of y over x. So that's just a concrete example of a domain R2 and two different coordinate systems there. Okay. And so the kind of problem that we're faced with is given z equals a function f of x and y, so some formula involving x's and y's in there, right, algebraic formula or something involving x's and y's, how to find not the derivatives dz dx and dz dy, because we could obtain those straight from the formula given for the function, but how to find dz dr and dz d theta. Okay, because x and y can be expressed in terms of r and theta, so then is there a nice way to express how we find those two partial derivatives? Okay. Okay, so that's a quick intro to the polar coordinates. I think you did see those last year as well. Okay, so it's just locating a point in the plane, either using the usual Cartesian coordinates x and y, or the polar coordinates r and theta. Yeah, but as I say, there's not really, I didn't really put down anything there that isn't in the notes. Okay, so we need to derive some kind of a chain rule for functions of more than one variable, for functions of two or more variables. And the stepping stone we're going to use to show how it's derived is we're going to use the small increments formula that we looked at last time. So this derivation starts towards the bottom of page 13. So I'll switch over to the overhead so we can have a look at that. Do this using transformation functions. Is that it? It's an answer to the question. How do How do you express the Cartesian coordinates in terms of the r and theta coordinates? You do this using transformation functions. Okay. Okay, I'm going to switch back to the notes now. Well, I'll stand them in afterwards as I remember. Okay. So looking here on page 13, so we set it up in general. So we suppose we have, so it begins here just after those polar coordinate equations here. So suppose we have a function, suppose we have two coordinate systems for the plane. So x and y, you can think of those as the normal Cartesian coordinates, and some new pair of coordinates s and t, say. So you could think of those as being r and theta. And you've got two functions, a u and a v, that give you the transformation from the new pair of coordinates s and t to the old pair x and y. Okay, so you've got two functions, u and v, that tell you what x and y are in terms of the new coordinates. Okay, specific examples were what we just wrote down for the polar coordinates, the two functions u1 and u2. And here they're called u and v. And if we have a function z equals f of xy, okay, that defines the third variable z as a function of x and y. But of course, if you substitute for x and y using the functions u and v, you then get a composition of functions which will give you z as a function of the variables s and t. Okay. Because you're replacing x with some expression in s and t, you're replacing y with some other expression using the function v of s and t. So you do have z as a function of s and t as well. And we want to find a neat way of expressing dz ds or dz dt in terms of the transformation functions u and v and the derivatives of the function. Okay. So what we start with in equation 1.80 here is the small increments formula. Small increments formula that tells us that the change in variable z induced by changes in the variables x and y is approximately this linear expression in the changes delta x and delta y. And the coefficients are the partial derivatives of the function. Then supposing we divide across this expression by a small change in the s variable, by a quantity delta s. Okay? So just simply dividing both sides of this approximation by delta s. So on the left-hand side, we have a ratio of changes, delta z, delta s, delta z over delta s. And on the right-hand side, we still have the coefficients df dx, df dy, those partial derivatives of the function f. Then we have these new ratios, delta x over delta s and delta y over delta s. Okay, so that's obtained from the small increments formula. And then to convert it to partial derivatives, what we do is we consider letting the quantity delta s approach 0. But see, on the left-hand side, we had delta s divided by, delta z divided by delta s. That's a ratio of changes. The change in the variable z divided by the change in the variable s. Okay? Now z depends on s through the variables x and y. So if we have that ratio of change in values, and we let the delta s tend to 0, what we're going to get on the left-hand side is the partial derivative dz dx. Okay? Because you're looking at the change in value of the variable z relative to change in value of the arguments s here. When we take the limit of that as s approaches 0, that's exactly the definition. Exactly the definition of the partial derivative dz dx. Just like we defined the partial derivative using limits at the start of this chapter, our first lecture. And similarly speaking, on the right-hand side, okay, the df dx and the df dy, they stayed the same. But the other ratios, delta x over delta s and delta y over delta s, they also, in the limit, become those partial derivatives, dx ds and dy ds. And because we're looking at the change in variable, the change in value of the variable s approaching 0, the approximation given to us by the small increments formula becomes better and better as you consider smaller and smaller changes in the variable s. Okay? So that in the limit, it actually becomes an equality of of these partial derivative expressions. So that was all done with the variable s. In the very same way, you can start with the small increments formula back at equation 1.80. Starting with the small increments formula, you can then divide both sides by delta t instead of delta s. Dividing both sides by delta t, then run through the same argument, will bring you to this second chain rule equation for the partial derivative dz dt. So for a function of two variables x and y, and a new coordinate system s and t, these two equations here, 1.82 and 1.83, these are the chain rule equations for that transformation. Okay? And what they do is they express the derivatives of z with respect to the new coordinates in terms of the derivatives of f with respect to the old coordinates, x and y, and the derivatives of the transformation itself. Okay? dx ds, dy ds, dx dt, dy dt, those derivatives can be worked out from the functions u and v. Oops. From the functions u and v that describe the transformation from the new coordinates to the old coordinates. Okay. So definition 1.5, this is the chain rule for functions of two variables, is given there. Now that was all for functions of two variables, but nothing special about the two variables. Just expanding that argument and just applying it to functions of any number of variables, you get the general chain rule. Okay? So you get the general chain rule in definition 1.6. If you set n equals 2, if you set n equals 2 in definition 1.6, you get exactly what we just looked at, chain rule for functions of two variables. Okay? So in the same way here, we have the variable z as a function of n variables, x1 through xn. And then a new set of coordinates, s1 through sn, and functions ui that describe the transformation. Okay? One function u for each of the old variables x. You've got x1 equals u1 of the new variables. x2 equals u2 of the new variables. x3 equals u3 of the new variables, and so on. And then you've got the chain rule equations. Now if you look at this equation here, it says dz ds is equal to the sum of df dxj times delta xj dx. Now the variable I, the index j in that equation is a summation index with the summation in front, whereas the index I is just an index of the whole equation. So you've actually got n of these equations. One of these equations for each of the variables. Okay. Maybe I'll show some of the expansions out of that that equation just to make it a little bit more clear. And then we'll jump into an example. Okay, so this is definition 1.6. So we'll just look at the form of the equations. Look at the form of the equations in 1.89. Might be able to capture some of this. Just because it's quite a compact piece, so I'll just repeat here, just to have it on the screen so you can compare it. This is just repeating equation 1.89. You don't have to take that down, so it's just repeating what's in the notes. So what would that look like when you start looking at it, at how it expands out? Well, if the index I was equal to 1, what it would say is dz ds1 is equal to, and I'll expand out the summation, df dx1, dx1 ds1, oops, S1 in the denominator there, plus df dx2, dx2, ds2, no, ds1 again, sorry, ds1, so it's always ds1 on the bottom here. Let me get it right, schools, df dx3, dx3, ds1. You keep having these terms until you get to the last one, which will be df dxn, dxn, ds1. Okay? So this tells you what the derivative of the variable z with respect to the new variable s1 is in terms of all these derivatives of f with respect to the old variables, xj, each of those multiplied by the derivative of that old variable xj with respect to this particular new variable s1. Okay, and then you'd have the second, so that's the first of the chain rule equations. There's n of these. This is for I equals 1 to n. There's n of these things. So when I is 2, you've got ds, dz, ds2. This is df, dx1, dx1, ds2. Now it's s2s in the denominator all the time. All these terms until you get to the last one, df, dxn, dxn, ds2. That's the second of the chain rule equations. And then you've got the very last one. The very last one happens when I equals n. You've got dz, dsn. So again, df, dx1, dx1, dsn. All the way to the last one, df, dxn, by dxn, dsn. Okay. But all of those are, all of that is just all contained in this compact description of the top. Okay. So we have the summation over the indexes j. That's the summation that's happening on the right-hand side of those equations there. And the term you're summing follows this pattern. It's always df, dxj, dxj, dsi. This equation, there's n of these equations for I equals 1, I equals 2, all the way to the last one, I equals n. But it's just, we're not talking about any particular case here. This is just the general form of these equations. So we'll look at let's look at a particular case now. So this is an example 1.10. So example 10 brings us back to the Cartesian coordinates and the polar coordinates in 2 dimensions. And it gives us a problem here. It says, so we're working in R2, and we've got this, this expression, f, curly f, is x df dx plus y df dy. Now this is some kind of expression, I'll just call it curly f. It's involving the Cartesian coordinates x and y and the derivatives of some function f with respect to those coordinates. What we'd like to do is translate or convert f into polar coordinates. So we're looking for some kind of expression. So what we're doing is we're seeking curly f, some kind of expression, and the kind of things we can allow in there is the new variables r and theta, or the derivatives df dr, df d theta. Some kind of function in those variables. Okay, because here it's the function in terms of the old Cartesian coordinates x and y. And what we seek is the equivalent expression for curly f, but in terms of the different coordinate systems we're playing. Okay, we can do this using the chain rule equations. Okay. So so the first of the chain rule equations would be, we could look at df dx, because this will, if we can get a nice expression for this, this will allow us to get rid of the partial derivative df dx. So that said, to get df dx in terms of stuff involving r, you have to do df dr dx plus df d theta dx. There's another chain rule equation, which is df dy, and that's the partial df dr dy plus df d theta dy.
What did that say before the R2? Was it ln or in?
Just in R2, just kind of saying what the setting is.
Oh yeah, of course.
We're working in R2. So those are the two chain rule equations that should allow us, if we can work with the right-hand side and simplify the right-hand sides, we can then substitute these expressions for df dx and df dy into the expression curly f, and work on it a bit, see if we can simplify it, and see if we can get rid of all the explicit reference to x's and y's and replace them with references to r, theta, or derivatives, df dr, df d. Okay. So we're not working with a specific function f here. F is just a general function defined in the plane, and we're keeping that aspect of it. Okay. So the things we'll need to work on, so we don't know what f is, so you can't simplify df dr or df d theta anymore. But what you can simplify is these partial derivatives. Okay? You should be able to get a definite description of those from the functions for r and theta in terms of x and y. So r is the square root of the sum of the squares, and theta is the inverse tan of y over x. Okay, so we can obtain dr dx and dr dy. Okay, we'll need those. Putting in here. dr dx, okay, we can take the partial derivative with respect to x of this expression. So you can treat the variable y as if it was a constant, use the chain rule for functions of a single variable. So this will be 1/2 the sum of the squares to the power minus 1/2 times 2x. I.e., a neat way to describe that would be x over r. Okay, because the 1/2 at the front and the 2 here will cancel. We've got x over the square root of the sum of the squares. Nice simple expression for that is x over r. Now it is mixing the two, the old coordinates and the new coordinates, but we'll work with that for a moment. So similarly, you can show that dr dy is y over r. Okay, that should be the case because x and y both appear in a symmetric way in the definition of r. The derivative of r with respect to x is x over r. The derivative of r with respect to y should be y over r. Yeah, arc tan. Well, we can use a result that the derivative of dz of arc tan of z, this is a standard result, 1 over z squared plus 1. Standard derivative is kind of look up in the formula books. You can prove it fairly straightforwardly if you use the definition of tan as sine over cos. Take the derivatives and that, use the quotient rule, and you can derive that formula. But we'll just use it for now. So the partial derivative of delta with respect to x then should be, let's give myself room here, we can run into that, d theta dx. So let's differentiate the outside function first. So this is going to be 1 over y over x whole squared plus 1. Then we want to multiply that by multiply that by the inner function with respect to x. But there it's the function 1 over x, so that's going to be minus 1 over x squared. So this is multiplied by minus y over x squared. But that x squared, you can multiply into the denominator. And it's going to give you minus y on the top and y squared plus x squared on the bottom, which is, of course, minus y over r squared. d theta dx is this expression here. So we got dr dx and dr dy in terms of x and y's and r's. We got d theta dx now in terms of x and y's and r's as well. Minus y over r squared. And I'll just say similarly, I'll leave out the details just to make progress, but similarly, d theta dy, you do the same exercise using this standard result about inverse tan, you'll find that d theta dy is x over r squared. Okay, so note there's a minus sign in the d theta dx, but no minus sign in the d theta dy. But that's because y and x do appear differently in the definition of theta, so there's no reason to expect the two derivatives to look similar. I mean, they do look similar, but there's a difference between them. Okay, but now we have these four partial derivatives of the coordinate transformation, which I circled in blue there, in the chain rule equations. We now have each of them in a simplified form. So we can go and put those back into the chain rule equations. Okay, so we'll return to the chain rule equations now. So let's look at the one for df dx. Well, we just simplify them in. So df dx is going to be, so dr dx is x over r, so it's going to be x over r df dr minus y over r squared times df theta. So that implies that x times df dx, because that's what's in the chain rule equation, that's what's in the original expression curly f, x times df dx, this is going to be x squared over r squared, sorry, x squared over r df dr minus xy r squared df theta. So that's one part of the expression curly f. The other expression, df dy, on the chain rule equations, is going to be y over r df dr plus x over r squared this time df theta. But that implies that when you multiply it by y, which is how it appears in the expression curly f, when you multiply it by y, you're going to have y squared over r df dr plus xy r squared df theta. So now we've got the two parts. We've got the two parts that are added together. So yes, take this expression here for y df dy, and that expression for x df dx, and add them together to obtain curly f. So adding these together, we get something that hopefully we can move towards our final simplified form of the expression curly F. So we're adding together this plus this. So collecting together the FDR part, you've got x squared plus y squared over r. Oops. Then you've got plus df d theta. You add together those, but of course you see there you've got over r squared, you've got minus xy plus xy. So that actually is going to cancel to 0. So that cancels to 0 there. So you have the minus xy from the first equation and the plus xy over r squared from the second one. But this expression here will simplify as well, because in the numerator there, x squared plus y squared, that's r squared. The square root of radius, isn't it? So overall, this simplifies then to just r df df. So that's the final expression we were going for. Translating the expression curly f, which is expressed in terms of the Cartesian coordinates, into the equivalent description, but just now described purely in terms of polar coordinates. So this is a polar coordinate description as required.
Right, what minus y?
Sorry?
You know, on the top line, right? We've got minus y over r2.
Minus y over r2, well that's how the derivative comes out, so that was derived here. The minus sign came about because I was differentiating y over x with respect to x.
Oh, yeah.
That gave me minus y over x squared. Yeah, I was differentiating the reciprocal. So that's where that minus sign arose from. And that produces then cancellations here. 2xy terms. Any questions about that, or any other clarification I can give? I'm not sure. Now I'll be seeing you again in an hour's time at 11 o'clock. We'll look at the definition of what's called the Jacobian determinant there. Then I've got a further page of example problems that we'll work our way through in that class. Okay? I'll leave it up there now, yeah. So I'll see you again in an hour.